Let's go back to a physics example with definite integrals. Let's suppose we know the velocity of a falling body is v equals f of t is a function that is going to be sometimes positive and sometimes negative, say representing throwing a ball straight upwards at first and then letting it come back downwards. The acceleration due to gravity is 9.8 meters per second squared in the downward direction. If you treat upward as positive, downward as negative, you can think of the acceleration as being negative 9.8. And you can think of the velocity as being, hey, the integral of negative 9.8. If you integrate negative 9.8 as a constant function of t as an indefinite integral, you'd write it as negative 9.8 t plus c. That's a general antiderivative. But if you happen to know the initial velocity, and this would be the acceleration, so the integral would be the velocity. If you happen to know the initial velocity is v sub 0, when you plug in t equals 0 here, you've got to get the initial velocity. And when you plug in t equals 0, you get 0 plus c. C has to be the initial velocity. So I can write negative 9.8 t plus the initial velocity here. And let's pretend we've got a particular initial velocity. Oh, let's make it something that works out nice. How about 19.6 meters per second? Twice 9.8 is just trying to make numbers work out nicely here. So what's going on? We've got a ball in our hand. We're throwing it upward with initial upward velocity of 19.6 meters per second. Its velocity at time 0 is 19.6 meters per second. 19.6 meters per second upward. It's a positive velocity. But then the velocity is a decreasing function. The slope here is negative 9.8. The t-intercept of this is going to be 2, right? Negative 9.8 times 2 is negative 19.6. Negative 19.6 plus positive 19.6 is going to be 0. And then the graph would keep going down. Now, of course, it's got to stop at some point. It's got to hit the ground. But maybe we should pretend you're up on top of the IDS building in downtown Minneapolis when you throw this ball upward. And you throw it not straight upward, but maybe with a slight bit to the side, so it doesn't come down and hit the top of the building. It keeps falling down toward the ground. Okay, it should probably not be a rock or a baseball. Tennis ball, okay. All right, everybody's cleared out while you perform this experiment. You're not going to hurt anybody, okay? That's your velocity as a function of t. Our question is, what's the definite integral of this velocity from time 0 to time 5? And what does it represent? Let's calculate the definite integral in 3 ways. And you should be able to use any of these 3 methods. The definite integral of this velocity function from 0 to 5. First method is to think about the areas. Because it's a linear function, that's doable. If it were a nonlinear function, it would not be so doable. You'd have to use some other method, either a limit of a Riemann sum or the fundamental theorem of calculus. And in general, the fundamental theorem of calculus is going to be the way to go. But we will do one more limit of Riemann sums here. What's A1, the area of that triangle? 1/2 base times height. Hey, its area is 19.6. Should I think about units? You can. It might be helpful. Units of t are in seconds. Units of v are in meters per second. This 19.6 is in meters per second because that's a number on the vertical axis. This 19.6 has units that are the product of these units. Meters per second times seconds. This is in meters. Not square meters. I'm not talking about a literal area that you would draw and measure, even though I drew this. I'm thinking more abstractly of the units of this area as being the units of this axis times the units of this axis. They are units of distance or length or displacement. What's the area of this triangle? A2. 1/2 base times the height. What's the height? I got to figure out what that distance is there. Right, that'll be the height. That as a distance is actually going to be the opposite of f of 5. Why the opposite? Because f of 5 itself is going to be negative. So I need its opposite to get a positive distance. I could also think of that as the absolute value of f of 5. Either way is okay. In general, it might be less confusing to use the absolute value signs. Okay, let's do it the less confusing way. Absolute value of negative 9.8 times 5 plus 19.6. I'm just plugging 5 into the function. Negative 9.8 times 5 plus 19.6. So this is the absolute value of negative 29.4, which is positive 29.4. That's the height. And that's what's got to go right there for the area, 29.4. 1/2 times 3 is 1.5. The area of that triangle is 44.1. However, it contributes negatively to the integral. So maybe I shouldn't have taken the absolute value sign of that. I'm trying to make a conceptual point here. As a literal area, it's a positive literal area. Both of these are positive as literal areas. Positive 19.6 there, positive 44.1. To find that literal area as a positive quantity, I do 1/2 base times height. The height is the length of that side. It's not equal to f of 5 because f of 5 is negative. The function is below the axis. So I take the absolute value of f of 5, get 29.4 to find the actual area of this triangle as a positive quantity. But it contributes negatively to the value of the integral. The value of the integral is 19.6 minus 44.1. Now I could have thought of this as a negative height, so to speak, to begin with, and a negative area, so to speak, and really just done f of 5 and got negative 29.54 there and negative 44.1 there, and then added the results. It would have been okay. I would have gotten the right answer. And in fact, with Riemann sum approaches, that's essentially what you're doing, because even when the graph goes negative, you're still adding up f of xi times delta x. And f of xi, when f goes negative, can be negative. But it's still the same Riemann sum formula, right-hand sum or left-hand sum. Those are examples of things called Riemann sums. What's 19.6 minus 44.1? What, negative 24.5? Is that right? My arithmetic's okay, but I still feel like sometimes I might make mistakes, so I like to double check. Okay, yeah, negative 24.5. That seems to be the value of the integral if I've not made a mistake. What does it represent? Anybody want to say a one-word answer or maybe a three-word answer for what it represents? One of those two?
Distance.
No, I'm not looking for distance. I'm looking for but something else that starts with dis. Displacement. Change in position is the three-word answer. Its units are meters. But it's negative. It represents displacement, change in position. It's telling me that after 5 seconds have gone by, the ball is 24.5 meters lower than it started, because upward was positive, downward was negative. On the top of the IDS building, I throw it up, comes back down. It comes back down to where it started after 4 seconds, and then another second longer, it goes another 24.5 meters downward. Why is it back to where it started when x is 4? It's because the area of these two triangles is the same. And the integral from 0 to 4 should be 0 by symmetry. Let's do it as a limit, but let's use Mathematica to help us do it faster. So f of t is, oh, I used a v of t. I used inconsistent notation by hand. Maybe you noticed that. Now I also spelled calculus wrong here. Calculus. I should have used an f of t here. I mean, it's not a real big deal, but I should have done that. So there's my function f of t. Let's program right of n. Although it's probably a good idea to say what a and b are over here. Putting a and b in there like that does give me the flexibility to change them and have everything get updated. That's kind of nice. So right, use the palette here. There's a summation button. Right down here, boom. I goes from 1 to n. This is a function of n. That's why I'm using the underscore. F of a plus I times delta x. We talked about that formula for xi the last time. Delta x is b minus a over n. Times delta x on the outside. That'll do a right-hand Riemann sum. Semicolons just separate output. Effectively, they suppress output. They separate input, I guess I should say. I can enter this. Nothing, there's no output yet, but now if I plug in a number for n, like 10, I get an approximation to the answer. Negative 36.75, not the exact answer. If I plug in bigger values of n, I should get closer. What was the exact answer? The exact answer was negative 24.5, right? Negative 24.5 right there. Plug in 1,000. I'm getting close to negative 24.5. It seems like I did it right. Can I say what right of n is in general? Okay, it's having trouble there. Let's see. I think maybe it's having trouble perhaps because I'm using decimal points here. Let me change this to not having decimal points in it. I'm going to write 9.8 as 98 over 10, which I could also write it as, of course, 49 over 5. And 100, that's 196 over 10. Let's see if this helps it not make mistakes here. No, okay. Something must be, when that kind of thing happens, that means something probably has saved in memory. It's interesting that this is working, but that's not, because this usually works. Well, maybe n is, maybe n is saved in memory. Let me try clearing n. Okay, that worked. That's what right of n simplifies to. Could you have done that by hand? Based on what we did on Monday, you could have. Will you have to for the test? With help, maybe. I'd give you help. Maybe I'd show the steps and you'd have to give reasons for the steps. The reasons often do involve formulas like we talked about on Monday, like this one, that the sum I goes from 1 to n of I is n times n plus 1 over 2. Remember that one? Triangular numbers, talked about that on Monday. You'd have to know those things, or I'd have to tell you. I'll say you don't have to put that on your note card. I'd tell you that if you need it. What's the limit of that as n goes to infinity? It's a rational function of n. The degree of the top and the bottom are the same, 1, n to the first power. Look at the ratio of the coefficients of the highest powers of n. Negative 49, bring the negative sign up there, over 2. Negative 49 over 2, that's negative 24.5. negative 49 over 2. Limit will confirm it as well. Here's the syntax. I made an infinity sign by doing some magic here. Escape, I and F, escape. There's also a button on the palette over there. Escape, I and F, escape makes an infinity. Negative 49 over 2. What about a left-hand sum? How do I change things? Change the word right to left. Change 1 to 0, change n to n minus 1, and all of a sudden you got a left-hand sum. The right-hand sum and left-hand sum are different for any fixed value of n. Different formulas, ever so slightly. This one's got a 5 there, this one's got a negative 5. They do give you different values. I'll put a decimal point in there to give an approximation. They give different values, even when n is large. But in both cases, the limit as n goes to infinity is still negative 49 over 2, negative 24.5. So there's our second method. What's the third method? Third method is the fundamental theorem of calculus, which we introduced last time. I'll reintroduce it now. FTC. It is a theorem, so technically it should be written as an if-then statement. Basically, the if part goes if little f is a continuous function on a closed interval from a to b, and capital F is an antiderivative of little f over the interval from a to b, then the equation I'm going to write down holds. I'm using x as the variable, but I could have used t. This equation is true as long as little f is continuous, and as long as capital F has the property that capital F prime of x always equals little f of x for all x in the closed interval from a to b. Capital F is an antiderivative of little f over that whole closed interval, then this equation is true. So in the present case, when I'm integrating f of t from 0 to 5, f of t being negative 9.8 t plus 19.6, to apply this theorem, there's my f of t. I need a capital F of t. I need to figure out an indefinite integral of little f of t. Do it in your head. Negative 9.8 t squared over 2, right? Negative 4.9 t squared is an antiderivative of negative 9.8 t. You can always check that by differentiation. Antiderivative of 19.6 is 19.6 times t. Do I need a plus c? No. It doesn't hurt. But if you include a plus c, when you do your subtraction, it'll cancel, because it'll be in both spots. So you might as well take c to be 0. Notationally, you should write 0 and 5 with a vertical line like that. That is notation. That means evaluate this function first at the top number, then at the bottom number, and subtract. The function evaluated at the top minus the function evaluated at the bottom. Oftentimes, the bottom limit of integration is 0. And oftentimes, when you evaluate the function at the bottom limit of integration, you get 0. So you don't often, since when you subtract 0, nothing happens, you don't necessarily have to write what I'm about to write. But sometimes you don't get 0. So it is worth emphasizing that we really are subtracting this, even though that's a big 0. 5 squared is 25. So we've got negative 4.9 times 25 plus 19.6 times 5. There's our old friend, negative 24.5. We got the same answer. And in general, the fundamental theorem of calculus is the way to go. Because in general, the areas you might want to try figuring out from a picture will not be simple rectangles or triangles, because there'll be areas under curves. I mean, if it's a semicircle, you could do it, because the area of a semicircle is 1/2 pi r squared. If that were the graph of the function, you could theoretically do it, but in general, you can't do it. You also don't, in general, want to do limits of Riemann sums, because even though you might be able to find a Riemann sum, and that comes up on the homework, it already has come up on the homework, finding left and right Riemann sums to approximate the areas, they don't give you exact answers, and finding the limits of them is, in general, a lot harder than the problems we've done so far. Because formulas like this don't work when you are adding up things like cosine of I or something. What's the sum? I goes from 1 to n of cosine of I. I don't know. Okay. So in general, that approach, though it does work for some simple examples, including even t squared, it's not what we want to do. In general, we want to use the fundamental theorem of calculus. I do want to do one more quick example, but let me just mention one word of warning, however. FTC, great as it is, and it is a theorem, so it's always true, there are circumstances where this is not helpful either. So what do you do when even this is not helpful? You have to fall back on approximating the integral with the sum and not taking a limit. You have to sometimes. When is this not helpful? It's not helpful when you can't figure out what capital F is. That's when it's not helpful. Maybe capital F is a function you've never heard of before, and so you don't even know what it is. That does happen. Plenty. Okay. So it's still true. It's a theorem. It's still true, but it's just not helpful in some circumstances. Though it is plenty helpful in many circumstances.